Hello. I've been using a title that might look like clickbait because addressing the nature of reality, it's kind of an ambitious project. In philosophy, this is a very hard question. Some people have said some clever things about the topic, but if you look at these things in all its generality, there's lots of difficulties regarding what the term people are using really means. And but if you restrict yourself to something more specific like the real numbers, well then it's possible to argue in a more rational way, or to to make some progress, I would say. And often when there's something that is uh, is interesting, when there's a video about some of those mathematical tricks that are nice and original, you will see a lot of example of people talking about them because they're kind of well known. I can assure you that you're not going to find anything similar to that uh, explanation. I've been struggling actually to find that explanation for 30 years because I was uneasy about things I learned at university, and but what I've learned at university was actually mathematically correct. And so the problem was more difficult than just finding a mistake in some kind of a mathematical argument. And I was able to come up with a solution which I found convincing for myself, but it was not that strong, and I was not actually able to convince people that I was right when I was uneasy with those results, because there was something wrong about the way we were using them. And then a few years ago, I studied mathematical logic, and I found that the solution was known for a very long time, and the solution is extremely powerful. It's much more powerful than what I was trying to argue. And so and so now there's no doubt that now I know the answer to this paradox, and it has to do with the notion of infinity. And so I'm going to use this to talk about the nature of reality, in the sense, can we say that the real numbers are real? Do they really exist? Is it something about reality? And it's interesting because when I was talking about the numbers, I came up with this nice story, which actually is part of my argument. So I said, you have the natural numbers. And I like that name. They're very natural. They're grounded. They exist. 0, 1, 2, 3. You can count apples and things like that. And people that would say that, this is not something about the universe in which we live, but this is something completely alien to our reality, the idea of number. Yeah, I'm not going to argue with that person, because we need to have some common ground about reality, and it seems kind of obvious that those things exist. And so when I want to talk about the real numbers, it's the same way. The real numbers are real the same way, and the pun is intended, as the integer. And the story goes the following: is the integer, they're not all numbers, and there is some missing part. Obviously, the negative number, for example. And so it's possible to prove that, if you don't know anything about negative number, it's possible to prove that something is missing by having a theorem, a statement that says that things do not exist. Like, there is no number such that if you add 1, you're going to get 0. Actually, in many of the axiomatization, that's actually stated as a fact to start with. And so you can prove that there is no negative number, or if you don't know anything about negative number, well, there is no inverse for addition. But then this is a proof. Those things, they don't exist. So there's nothing wrong by talking about an extension of the natural number and adding the stuff which is missing. And if you add -1, and this is a new object, and so there's no contradiction, it's a new object, it's not a natural number, the new set that you have, well, you're going to get the integer. And you can do that also for fractions. So with the integers, there's something missing, but you don't know about the fraction. It's missing in your universe, and so but you can prove that there is some things that do not exist, like in that case, the inverse. And in the case of the negative, you can add -1. For the inverse, you would have to add some kind of a function that would be like 1/n, but it's easy. You add that. It was not there, so there's no contradiction. You have a new set with new numbers that you have invented, and now you have the fraction. And of course, you're gonna still find missing stuff. The Greek were traumatized by that. Square root of 2, the diagonal of a square, it's actually not irrational, and so it doesn't exist, and you can prove that it doesn't exist. Now it's more complicated because if you add square root of 2, there's a lot of stuff still missing. But I'm not going to go into that because my point will be that when you deal with the real number, at some point it's kind of becoming arbitrary, and you see what I mean. It's going to be part of my argument. But then from the real number, the missing part would be, square root of -1. And so you can prove it doesn't exist. Then you can add it without a contradiction by saying that that's a new thing that you add to have a new set. And then you have the complex numbers. So what about the real number? Well, the real numbers, they can be defined in many different ways. And all the set before the real numbers, and now you need to know about Cantor's theory at least a little bit, those sets are countable. So when you start with the integers, they're the definition of what can be counted. But when you get the natural number, when you get the integer, well, there's as many integers as natural number, because you can count the positive and negative integers by making a pairing. You must know that trick. So there are as many. This is the same infinite. And when you go with the fractions, that's the same thing. The pairing is more complicated, but they are countable. But then that's a very basic fact of set theory. The real number, they're not. Absolutely not. There's so much more real numbers that it's just like they're the countable number. They are just like the exception. And they're a tiny little fraction of all the real numbers. And that's the standard definition of the real numbers. But what if I choose another one? Why not? Let's play with that concept. And so I'm going to introduce another definition of a real number. I'm working in a computer science department, so why not define the computable real numbers? It's not exactly my idea. This is a concept that is known. Those would be the number that can actually be computed. Like you give to the computer program the position you want to know, and it's going to be computed. You can compute the decimal of p, square root of 2, the golden ratio, like all of them. Obviously, all of them, because if that number cannot be printed, expressed, if there is no algorithm to actually give you the number, it's kind of weird. So the computable real number, in practice, there's not much missing. Of course, if you know about these things, you'll say, yeah, there's a lot missing. I know where you're going. I know the argument, but in real life, you never find anything missing, because the number that is missing, you would not be able actually to use it to do anything else in terms of computation. It would be a number that is unknowable. And so they're kind of lacking some sort of utility, those numbers. But the thing with the computable real numbers is that they have to be very different from the real numbers, because they are countable. So there's as many computable real numbers, as rational, as integer, and as natural number. They're all the same infinite. And the standard definition would say that the real number, they are not like that. There's much, much, much more of them. But the thing is that those two different definitions, which are supposed to be so different, they will never make any difference in your life if you are doing computer science, biology, algebra. You will never actually in practice or even in most of the theory except logic have to deal with a number that would not be computable. And of course, in my class of theoretical computer science, I teach the existence of those numbers. They actually do exist. There is actually a number which would be extremely useful. We call it omega. That would be a number that would be very useful if we could compute it. And unfortunately, it's not computable. So I know that the definition of computable real number is not equal, but there's some possibilities for using other definition, and having the real number to be defined as the computable real number would not change my theoretical class. It would not like, oh my God, I have the wrong definition of the real number. What am I going to do? Because it would even make my life easier. That number, I would just tell them, it's not a number. I would just tell them, don't try to get that number, okay? You might think that it exists, but it doesn't exist. And in that context, it would mean that it's not computable, so you will never get that number. And that would be a different perspective, but that would lead to the same thing. You know, the number is not computable, you will not get it in both of those universes. But it goes further than that, because, and that's the thing that I was not aware of, which actually blew me completely away. Like I was, oh my God, this is so deep, is that it is known that if you deal with objects and you have an infinite number of them, like the integer, the reals, and things like that, when you have first order logics and things like that, well, the thing is, I'm going to explain it in lame word, but those objects, they live in some universe. I'm trying to argue about the real number existing in our universe. Well, that's a universe. They call it a model, actually. And the statement is absolutely incredible. Any mathematics, which an infinite number of objects, there is always a countable model. Okay, what does it mean? Well, there is always a universe in which your object exists, and that's a thought experiment. That's a universe you can think about. It doesn't have to be your universe, but it exists. And in that universe, there is only a countable number of objects, like the integer, the rational, and things like that. And this result applied to set theory, even with the axiom of choice, which means that all the theory of those infinite that are larger and larger, like the set of natural number, and then you have the set of real number, which is strictly larger in terms of infinity, and then you have the function from the real to the real, which is larger in terms of infinity. Well, all of that can live in a countable universe, basically can live in a universe where there is no such thing. And you will never get any problem with that. You will never get into any contradiction, because that's a well-known statement of logic that is accepted. There is a model like that. And so the fact that you don't get a contradiction when you talk about infinite that are larger in size than the countable, and the fact that you don't get any contradiction by doing that in a universe where there's no such thing, basically lead me to think that those things do not exist for real. That would be a way for me to separate the notion of existing for real and being a mathematical concept. So for me, those infinity, they don't exist for real. It doesn't mean they're not useful. They are amazingly beautiful and useful, but they're not real. And it's not a big deal. It's just that they're not real. And so the real number, there is some issue there. And I'm led to believe that if I decide, this is my decision, to use this way of defining reality, this way of deciding what's real and not, well, then I have to accept that the real numbers are not real, which is not the end of the world. It doesn't lead to contradiction. But even though I was not talking about that in this video, it actually solved a practical problem I was facing, which is it rendered an argument in theoretical computer science. It really shows that one argument I was told when I was younger is incorrect. And that would be the only exception to that. And maybe in another video, I'll point the example I was referring to. So, yeah, so let me finish by saying, that's just a thought.